Dear students, in this video lecture, we are going to discuss about digital to digital conversion. That means digital data to digital signal conversion. So what are the techniques are there to convert digital data into digital signals? Those techniques we will discuss in this video lecture. So this is the first topic of Unit 2, classroom discussion topic. Okay. The classroom discussion topic 10, the first topic of the second unit, we are going to discuss about digital to digital conversion. Okay. In this classroom discussion topic, we have the lecture outcome. After listening to this video lecture, you as a student will be able to interpret digital data into digital signals. After discussing about different techniques, how the data is converted into signals, then you know very well so how to convert from signals to data to signals. So what is digital to digital conversion? Digital data to digital signal. How we are representing the digital data into digital signals. For that, three techniques is there: line coding techniques, block coding techniques, and scrambling. These three techniques will be used for represent the digital data into digital signals. The line coding techniques we are maximum used to represent the digital data into signals, but block coding and scramblings maybe or may not be we are using. But all three topics we are going to discuss in this CDT. First one, what is line coding? Line coding means converting a string of ones or zeros, that means digital data, into a sequence of signal that denotes the ones or zeros. Okay. So example, if here is there high voltage level plus V is there, no? So if example I represent 1 equal to positive voltage, okay, 0 equal to negative voltage or low voltage, okay, 0 equal to low voltage or negative voltage. So like that we are going to represent some form of representations. So here what are the things required for that? Line encoding and line decoding. Why? Because the digital data will convert into digital signals, then signals will be converted into digital data. Okay, data to signal, signal to data. So for while converting data to signal, we need encoder. While converting signals to data, we need decoder. Okay. So here, mapping data symbols and signal levels. How we are mapping it? So while we are representing the data symbols, that means zeros and ones, it's a combinations of bits. Okay. So 1 or 0 are combinations of 2 bits, 0, 1, 1, 0, 1, 1, 0, 0 like that. Or it may be the combinations of 3 bits, 0, 0, 0, 0, 1 like that. So number of bits according to number of levels. Okay. The data symbol can be encoded into single signal element or multiple signal elements. You understood that? Okay. What they are saying? A data element can represent with single signal element or multiple signal elements. So how we can represent this diagram? So how it is there? Not diagram. So 1 will be represented that positive voltage, 0 will be represented for negative voltage. Okay, like that we can represent, or otherwise 1 may be represented that positive voltage to negative voltage, and 0 may be represented that minus negative voltage to positive voltage. So both it will be represented like this. So we can have multiple elements to represent single data. The ratio R is number of data elements carried by the number of signal elements. Okay. So how we are identifying the R? That is the number of data element by number of signal elements. You just remember it. That will be useful to find how to convert the signals. The relationship between the data rate and signal rate. Okay. So what is the relationship here? The data rate defines the number of bits sent per seconds. That is bits per seconds. Per second, how many bits are transmitted? Already we have discussed what is bit rate. Okay. So now signal rate. What is signal rate? Number of signal elements sent in a second. Okay. In a second, how many signal elements are sent? It may be represented using bars. Okay, bar. It is also referred as modulation rate or pulse rate. Okay. Modulation rate or pulse rate or this number of signal elements are transmitted. So what is our goal? Goal is to increase the data rate while reducing the baud rate. So that means we have to increase the data rate. Data, we want to send maximum data with less signals. Okay, that is our goal. So now we are going to discuss about how to represent it, signal element versus data element. So here we can say that baud rate also. Okay, so pulse rate I told no same thing. You can use that baud rate also. Baud rate or pulse rate or modulation rate. How we can represent the signal elements versus data element? So you see there in this first diagram. Okay, so example, this is the timeline, black line. So you just here, this is the positive voltage, this is the negative voltage. You just assume it. Okay. So if I want to represent, whenever 1 it is there, that will be the negative voltage. Whenever 0 is there, that is the positive voltage. Okay, for this entire diagram. So like this diagram, I am taking that I want to represent for 1 as a minus voltage, 0 as the plus voltage. Okay. So one data element, one signal element. So this is minus voltage, 1 is there, this is minus voltage. Whenever 0 is coming, that is plus voltage. Like that I am designing. So what is the R value, ratio value? Number of data element, here 1, number of signal elements, that is 1 by 1. So R equal to 1. In this diagram you see here, what will be happen? So for example, this is minus voltage, this is plus voltage. You consider like this. If 1 is there means what I am going to do? Minus voltage to negative voltage. So I am using both minus voltage and plus voltage. But what I am doing it, whenever I am saying data 1, it will be shifted from minus voltage to plus voltage. Okay. Then if in case 0 is there, so what I am going to do again? So same thing. So whenever the data is there, it's taking two signals to represent the single data element. Okay, that is identification here. What will be happen? So here minus voltage plus voltage is there, then it will be represented only one data element. So one data element by two signal elements. Clear? So here this third diagram you see here, C diagram C. What will be happen? Two data element, one signal elements. Okay, so it may be positive voltage, it may be negative voltage. So if this two data element converted to positive voltage, whenever it is coming here, same single signal elements with represent the two data elements. So what is the value? 2 by 1, R equal to 2 by 1. So here you see this 4 data element used for 3 signal elements. Okay, so 1, 2, 3. Okay, so 4 data elements by 3 signal elements. So R equal to 4 by 3. Just remember how to calculate R value. So while we are calculating data rate and baud rate, the baud or signal rate can be expressed as using this formula. Okay, signal rate equal to C into N into 1 by R. What is the C value? C is the case factor. Worst case or best case or average case. Okay, worst case the value is 0, best case average value is 1, average means 1 by 2, 0 plus 1 by 2. So now N value, that is N is the data rate. Okay, so R is the ratio value. So now we are going to calculate the signal rate. The signal is carrying the data in which one data element is encoded in the one signal element. One data element by one signal element. So what is R value? 1. So that's why they are given 1. If the bit rate is 100 kbps, what is the bit rate? N equal to bit rate. Okay. So 100 kbps means 1 lakh bits per second. 1 lakh bits per second. Then what is that average value of the baud rate? If C between the 0 and 1. Okay, so then we can take the average. C equal to 1 by 2. So 1 by 2 into 1 lakhs, that's a data rate into 1 by R. R value equal to 1. So finally we are getting 50,000. 50,000 means 50 kilo baud. Signal rate always represent using baud. Okay. Although the actual bandwidth of a digital signal is infinity, the effective bandwidth is finity. So here, this example, you just see that the maximum data rate of the channel, how we can calculate is N max equal to 2 into B log 2 of L. Okay, this is Nyquist formula. Already the formula is defined. So how we can reframe it? Example. So here what they are saying that a signal with L levels, if any signals have L levels, actually can carry log 2 L bits. Okay, so how many bits it will take? Log 2 L bits. So this we will identify how many levels, how many bits. In that we can use this formula. So the N max equal to 1 by C into B, that is bandwidth into R, that is ratio between the data rate and data element by signal element. Okay, so here rate may be calculated as per the levels log 2. So while considering the line coding techniques, so choosing the good signal element referred to as the line encoding. So line encoding, what are the problems are there? That we are going to discuss about. Baseline wandering. What is baseline wandering? A receiver will evaluate the average power of the received signal and use that to determine the value of the incoming data elements. Okay, so it will take the receiver. What it will do? It will evaluate the average power of the received signal. Then it will check that the incoming data elements are, they determine the incoming data elements. If the incoming signal does not vary, okay, so example, if it is coming continuously same value, there is no changes are there, means long period of time, if it is coming like that, means what is the meaning of that? Baseline will trip and thus cause error in detection of incoming data element. There is no changes in the signal means that some errors may be occurred. We can fix it accordingly. Next one is the DC components. What is DC components? DC components means when the voltage level remains constant. Okay, so voltage level remains constant for long period of time. There is an increase in the low frequency of the signal. What is the meaning of that? If the example, the timeline is there, it is plus voltage. Okay, this long period it is constant. It is not changing. Always 1 1 1 1 1 1. It is coming. Okay, that is also considers the DC components that will be generated as low frequency. Okay, so what happen normally? Most channels are band pass channel and may not support low frequencies. So example, if in case you are sending voices through telephone line, so minimum 200 cuts should be there. If below 200 cuts, if you are sending any signals, the signals not able to process in the telephone line. Okay. Self-synchronization. What is self-synchronization? So the clock at the sender and the receiver must have the same bit interval. If I am sending 10 bits means the receiver also receive 10 bits. The clock should be synchronized. Otherwise, the bit may be interpreted with miscommunications, like misinterpretation may be happen. Okay. So example, see here, it is sending data. For 1 it is sending like this, 0 is sending like this. So in case the signals crossed sometimes, okay, the clocks are not synchronized. Here the clocks are here, okay. So but this up to this point it is there, but clock is not synchronized here. What happened? So the misinterpretation will be there. Here positive voltage, here negative voltage is there, but here what happened? This one may be converting from positive to negative, then zero may be some misinterpretation will be there in the receiver side. So for that we need this synchronization. Example, a digital transmission, the receiver clock is 0.1% faster than the sender clock. Okay. So how many extra bits per second does not receiver receive if the data rate is 1 kbps? How many if the data rate is 1 mbps? Okay. At 1 kbps, the receiver receives 1001 bits per second instead of 1000 bits per second. Yes or no? 0.1 means 1 bit extra it will get. So instead of 1000 bits, it is getting 1001 bits means how many bits are extra? So if in case of 1 kbps, that its rate is more 1 megabits per second. So what will be happen? Then 1000 bits may be received extra. Okay, 1000 bits means for every kilo it's getting 1. So then 1000 bits it is getting extra. Okay, finally error detection. So in this method there is no error detection, but what happened? Error occurs during the transmission due to line impairments. Okay, so in case impairments is there means error may be occurred. Some codes are constructed such that when an error occurs, it can be detected. For example, particular signal transition is not part of the code. Okay, so that error correction, error detection method is there. When it is occurs, the receiver will know the symbol error has occurred. Okay, so example, it is sending some signals. It is misinterpreted the values means that the receiver will understand that some errors happen due to interferences. So next one is noise and interference. There are line encoding techniques that make the transmitted signal immune to noise and interference. This means signal cannot be corrupted. It is stronger than the error detection. Okay. Complexity. The more robust and resilient the code, the more complex is it to implement, and the price is often paid in baud rate or required bandwidth. What is the complexity? We can use how much signals we are sending, which line coding techniques we are used. Accordingly, we have to pay more amount. So, dear students, now I am stopping my video presentation now, and I will continue line coding techniques for digital to digital conversion in the next video. So, thank you very much for listening it.